This lecture will be about SMT solving, and we will say something about the syntax and the tools. We already saw that SAT is satisfiability, that is about propositional formulas. That is composed from Boolean variables and operators, negation, disjunction, conjunction, implication and by implication. And SMT means satisfiability modulo theories. And that is about SAT extended by extra theory. And here we focus on the theory of linear inequalities, either on real numbers or integers, but they deal with numbers. Again, a formula is satisfiable, abbreviated to SAT, if it is possible to give values to the variables such that the formula yields true. And the mapping of the variables to these values such a way that the formula yields true, that's the satisfying assignment. Let's give an example. Here we have a formula on integer variables a, b, c and d. 2a is greater than b plus c, 2b is greater than c plus d, 2c is greater than 3d, and 3d is greater than a plus c. Well, you may try to find a solution by yourself, but you will see that it is not that easy. It has a solution, it is satisfiable with satisfying assignment. A is 30, b is 27, c is 32, and d is 21. And in fact, this is the smallest solution. There are tools to solve this kind of problems, and for checking satisfiability we have several powerful tools, SMT solvers like Z3, Yikes and CVC4. And for non-commercial use they are free to download and free to use. And you can see further instructions how to do this. You can also Google them and find also how to do this. Most of them have their own syntax, but luckily they all accept the syntax of the SMT lib standard. In fact, there are also competitions, and if you do a competition on several tools, of course they should have a common syntax. And in this lecture we show how to use the syntax of SMT lib version 2. There was an earlier version 1.2 and it was slightly different, but now the focus is on version 2. The tools allow to be used interactively, but we want to apply them on big formulas. And a big formula you do not want to type in yourself, but you want to have in a file. And typically we have a program generating this formula in a file. If the file is called, let's say, file, then we will call the tool by typing the name of the tool and maybe some flags in some command line interface, and that is how we use the tools. The general ingredients of a file in the syntax are as follows. It starts by set logic or set options, where you can define which logic to use or which option to use. And most times they have a default, so they can be left away if you just want to take the default. Next you have the declarations. You can declare variables, you can declare functions, and you do that by declare const and declare fun. And next we have the actual formula, and this is put in assert with parentheses around it. And between the opening parentheses and the closing parentheses we have the formula that may be very big. Next we have the command check SAT to do the actual SAT solving. In case of satisfiability we want to show the satisfying assignment, we should continue by get model. All operators in this syntax, greater than, less than, equality, greater or equal, less or equal, plus, times, and, or, not, all operators are written in prefix notation. That means always first we start by parentheses open, then we have the operator, then the arguments, and then parentheses closed. So in these notations the expressions 2a is written as parentheses open star 2a parentheses closed. And b plus c is written as parentheses open plus b c parentheses closed. And the full formula 2a greater than b plus c is written as follows. We simply take these two ingredients and we put parentheses open, greater than around it, and we conclude by parentheses closed. The operators plus, and or may have any number of arguments, not only two, and that's often convenient if you want to add a great amount of numbers, or if you have the conjunction of a great number of requirements. You only need to put a single one plus at the start or a single and at the start. For linearity, star always has two arguments, and one of which should be a number, otherwise the expression is not linear, and then typically the tools do not accept it or are very poor. So our problem of solving 2a greater than b plus c and so on can be expressed by the following formula. First we have the declarations of a, b, c and d, all being integers. Next we have the assert of the whole formula, which is an AND of the four requirements, each expressing such an inequality. Then check SAT and then get model. And if we put this text in a file called file, for instance by doing cut and paste from the examples document, then we call Z3 with the flag minus SMT2 to state that we need this SMT2 syntax, and then the name of the file. Then within a fraction of a second we get the output SAT and the model stating that B has the value 27, A the value 30, C the value 32, D the value 21. Indeed containing the values as just mentioned. The same can be done by one function f instead of four separate variables a, b, c, d, just by replacing a by f1, b by f2, c by f3 and d by f4. And then it looks as follows. First remember that f1 is written in the SMT syntax parenthesis open f1 parenthesis closed. It follows the same prefix format, always starting by parenthesis open, then the name of the operator, then the arguments and then the parenthesis closed. And the full formula then reads as follows. And if we apply Z3 on that, we get the solutions, but now for f1, f2, f3 and f4. Well, here we have an example in propositional SAT. We want to check satisfiability of some big formula containing and or and negation and implication and by implication and four Boolean variables a, b, c and d. Well, in the syntax implication is written as implies and by implication by IFF. And then the formula reads as follows. We declare a constant of type bool a and the same for b, c and d. We have an assert and there we simply express the formula as given on top. And we conclude by check SAT and get model, and indeed this gives the solution. SMT solvers can also deal with very big numbers. For instance, if we want to compute 87 times a very big odd number plus 93 times a very big other odd number, and we want to divide it by 2, well, which is possible since both parts are odd, so the sum is even, so dividing by 2 is possible. So this should be an integer. If we want to compute this by the SMT solver, we can do this by the following formula. We declare a to keep the value, the first big number. We declare b to keep the value of the second big number, and c for the answer. We just say 87 times a plus 93 times b should be equal to c plus c. And if we do check SAT and get model, we get the result. C is indeed the result of this computation. A convenient operation is the if then else, abbreviated to ITE. It always has three arguments. The first one is the condition, which should be a Boolean. The second one is the result in case the condition is true. And the third one is the result in case the condition is false. Let's give an example. ITE less AB, 13, and so on. What does this mean? Well, this yields the value 13 in case A is less than B, and otherwise it yields the value 3a. And another application is as follows. We can do ite p10. What does this mean? Well, p is a Boolean variable, and in case this has the value true, it yields 1, and otherwise it yields 0. So this transforms true to 1 and false to 0. And if we do this for p, q, r and add all results, this just counts the number of variables among p, q, r that are true. This kind of things is convenient to use and will often used in examples. Summarizing, we saw how SAT can be extended to SMT to deal with linear inequalities. And the SMT solvers like Z3, YIKES and CVC4 accept formulae in the SMT lib syntax, and we saw a number of examples of this. And in next lectures we will give several applications, but you may start by playing around right now. Good luck!